All right, so this is sort of going to now round out our backbone derivative rules. We can take the derivative of a constant times a function plus another function, a function minus another function, a function times another function, divided by another function. We can take the derivative of functions that look like x to some power, that are just a constant, that look like sine or cosine or e to the x. And now we're going to look at another function like e to the x, but a little bit different. In fact, the inverse function of e to the x, ln x. And to do this and to compute this derivative, as you can imagine, we're going to use the definition of the derivative, like the limit as h approaches 0 of f of x plus h minus f of x over h. But in order to pull that off, we're going to need a couple facts, a few facts to make that happen. So let's see. So let's just run through the computation of this limit. So limit as a approaches 0 of 1 plus a raised to the 1 over a power. Okay, so we start looking at this, we could just look at it numerically. Let a approach 0 from the right, so you could plug in values like 0.01 or 0.001 or 0.0001, and you see that what comes out, 1 plus 0.0001 raised to the 1 over 0.0001 power. This comes out to be 2.7182. You could also approach 0 from the left. If you approach 0 from the left and you plug in a values of like negative 0.01 and negative 0.001 and negative 0.0001, this comes out to be 2.718 as well. And then you say, okay, this 2.718 seems to be interesting with respect to this limit. I claim the number 2.718 is actually quite interesting within the realm of mathematics, because if you recall from whenever we talked about e to the x, e may look like a letter, but it's just a number like pi. It's a number whose decimal expansion goes on forever, never repeats. It's a number whose value is about 3. It's a number whose value is 2.718, more or less. And in fact, this value is what's showing up from the left and right approach for this limit. So this limit here has a value of e. That's going to be something that's sort of going to be pivotal for us in terms of developing the derivative for our ln function. A couple other things that we're going to need, and these are just basic pre-calculus facts that you surely have seen from your mathematical past. Remember that whenever you are subtracting two ln's, like ln of anything minus ln of anything else, you could rewrite that as ln of the first anything divided by the second anything. You also have another limit, or excuse me, ln rule that says ln of anything raised to the power c. C here is any number. Well, you could just bring that c down in front and rewrite as c times ln of that anything. And as a final rule, remember the ln function is the inverse function to the exponential function. So when you take the ln of e, the result is 1. What power would you have to raise e to get e? That would just be 1. That's the basis for that fact there. Okay, so it's going to take all 5 of these facts, the 4 that are in the clouds of thought and the 1 that we computed via numerics for the limit, to compute the derivative of this. But with this in mind, we can proceed with the technicalities.